Okay, so organic chemistry does not mean the chemistry of growing produce without the use of pesticides. So, unfortunately, organic is one of those words that does have a mainstream um, definition that does not apply here. So, basically, organic chemistry is the chemistry of carbon. So every single organic molecule will have at least one carbon. And then we're going, as we go through the unit, so it's going to take, well, the first lesson, which is just hydrogen and carbon, is the simplest kind of molecule. We're going to spend a few days on that so you get the basics, and then basically we're just going to add stuff to the chain. So those of you that have taken or are taking 12U biology, you will talk about functional groups and stuff like that, but you don't usually name and draw them the way that we're going to. So as much as you'll be able to recognize it, we're really going to go way beyond what you would do in biology. Okay? So an organic family, if you happen to take a look at the calendar, it's listed by organic families. We're going to start hydrocarbons tomorrow. Then we'll do alcohols and ethers, aldehydes and ketones. Those are organic families. And the reason that it matters what kind of molecule or what kind of family it is because it's going to affect the physical properties. So what we're going to do is look at how to name and draw them. We're going to talk about their reactions, and we'll talk about important physical properties because we are organic molecules. Organic chemistry is essentially the chemistry of life. So if you want to go into a pharmacist or something like that, organic chemistry is important for that. Medicine, healthcare, and then even some branches of engineering. So many materials are carbon-based. We watched that little snippet about those carbon nanotubes. So even though that chemist wasn't necessarily trying to be a doctor, for example, he still studied the chemistry of carbon. So even in some types of engineering, organic chemistry will be very important. So because all kinds of materials like cellulose, wood, that is all based on the carbon atom. So last year in grade 9 and 10, we often said, oh, skip the column with carbon in it because carbon is so unique that it gets its own special unit, okay? Or section in a course. If you choose to continue in chemistry or physical sciences, you can take biochemistry, you can take entire courses on the chemistry of carbon or organic chemistry. It gets very complicated very quickly. So we're really just going to scratch the surface and focus on different functional groups, how our atoms are arranged, because that's going to affect polarity, which we already talked about, melting and boiling points, which are strengths of forces, like London dispersion and hydrogen bonding, dipole-dipole, we just talked about that, and their reactivity. So the topics we did last unit will actually help us with this. So the carbon atom has 4 valence electrons and can form 4 covalent bonds. So that will be important. Carbon always needs to have 4 covalent bonds. Sometimes they can be single, sometimes they can be double, sometimes they can be triple. Does anyone remember what kind of Vesper shape this is? 2 in the same plane, 1 coming out, 1 going into. Starts with a T. Yeah. Tetron or tetrahedral. So when you build giant organic molecules, they will all look tetrahedral around the shape, around the carbon. So we'll start with single bonds. They are and when we do hydrocarbons tomorrow, we'll start with single bonds as well. They are the simplest type of bond. So we are usually going to use dashes. We won't do bubbles, but you could do the same thing. So there are general classifications of organic molecules. If it's all carbon-carbon single bond, they are saturated. So saturated meaning their carbon atoms are bonded to the maximum number of atoms, like it's saturated with atoms. If you got stuck in a rainstorm, you would say, oh, my clothing is saturated with water. It's so much water. So when you have a saturated carbon, there is the maximum number of atoms. This matters because when we talk about reactions, the carbon-carbon single bond is very, very strong and very, very difficult to break. So when you use those model kits, I encouraged you to use the shorter ones that were tougher because that represents a tough single bond. Double and triple bonds, using those bendy long ones, they are easier to break, and that's why they're a little bit bendier. So this is just an introduction today. We will talk more about specific reactions, but when you go and try to decide what kind of reaction is going to occur, sometimes students are frustrated. Where do I look? How do I know? Generally speaking, you are not going to break single bonds. So you're going to look for a double bond or a triple bond, something weird in the chain. Okay, so then double bonds or triple bonds, sometimes they're classified together as multiple bonds. We call those unsaturated because you could break them. You can add more atoms to that carbon atom. So the double and triple bonds are not as strong. They are more readily broken and are more reactive. So when we get to the functional group that has a double bond or triple bond, that is going to be sort of the interesting part of the carbon chain. That's what you're going to look for when you're doing the reaction. Okay, so how do we decide, what are we looking for in general when we're talking about organic molecules? So once we move past Monday or Friday and Monday's lesson, and we start adding other atoms to the carbon chain, then we are going to get different forces. So dispersion forces, they are nonpolar. They are going to be the simplest type of force. And then once we get, say, an alcohol with an OH, an aldehyde with C double bond O, those are the kind of things, the weird things in the chain that you're going to be looking for. Is it polar? And then better than polar, can it hydrogen bond? Okay? So we're going to do that each time that we talk about a family. So we did just do this, but in case you forget, for hydrogen bonding, you need NO or F and an H. And then dipole or dipole-dipole would be anything that's polar. And then if it's nonpolar, it's going to be dispersion forces. Because organic molecules can be very large and complicated, and again, those of you in biology will have looked at this, you can have more than one section in a molecule as well. So in grade 11, we do the change in electronegativity. But then in grade 12, we're kind of trying to expand that. looking at a large molecule and deciding what parts are polar and what parts are not polar. The good news is with organic chemistry, not even F really. It's going to be carbons, hydrogens, nitrogens, and oxygens. Okay? So they'll just be in different spots. So nonpolar bonds will occur when there is equal sharing, as you know already. So carbon, carbon, and carbon hydrogen, which are the basic backbone to every organic molecule, are nonpolar. So the electronegativity difference is very small, and you'll still get that periodic table with those electronegativity values on there. But again, when we do organic chemistry, it's basically carbon and oxygen, nitrogen, maybe a halogen. Okay, so really, really simple types of atoms. It's just arranged differently. So once you start bonding a more electronegative atom, such as oxygen, nitrogen, or a halogen, the unequal sharing of electrons creates a partial difference, which increases the polarity. So sort of similar actually to the last unit. Once you decide if something is polar, then you can also relate that to the strength of the intermolecular forces. Once it's more polar, the intermolecular attraction will also be stronger. And without giving you real accurate kilojoule values, how do we discuss in general the strength of the intermolecular forces? Usually we talk about melting and boiling point, kind of similar to the last unit. So the increasing strength of the intermolecular attraction, we are going to do basically the same thing. Okay, and of course chemists are lazy, so we use MP, BP. So if you printed off all the notes and you happen to take a look at it, you would have noticed that it's very structured very similarly. You do the naming, you do the drawing, you talk about properties, and eventually talk about reactions. So basically, we're just kind of rearranging the atoms on the chain. Oh, huh, it literally says that on this slide. So increasing polarity, stronger the intermolecular attraction between molecules. So how are we going to recognize that? Increased melting and boiling point. So then again, we are looking for polarity, but also with polarity, can it hydrogen bond? And even though it's FON or NOF, right, you can include fluorine as well. That's just not a very common atom you'll see in organic molecules. So again, it's really repetitive. The number of bonds, how the atoms are arranged, that's what's going to be different. And we'll also talk about solubility in water. So if molecules are polar, then we say they are soluble in water. But many, many organic molecules are not soluble in water. So for example, when you go to pump gasoline into your car, gasoline is not pure, but it's a mixture of octane and decane. Octane is 8 carbons. And when it rains and you see a puddle of water at the gas station, usually you can see the oil droplets in the puddle of water, right? So it's difficult because in grade 11 we talk a lot about solubility in terms of precipitates, which is fine, but something can also not be soluble if it's a liquid. So when we do our lab next week, when you do the solubility section, you're going to look for droplets instead of chunks, instead of precipitates, okay? So it says here that hydrogen bonding will be increased melting and boiling point. This would be the highest. These forces are the strongest, which we just talked about, but if you would like to remind yourself. So this next slide just gives you a preview, really, of what we're going to do. So we'll spend tomorrow and Monday getting down the basics to this, and then we'll start adding stuff to the chain. So a functional group changes the properties of the molecule. So once you have double or triple bonds, then you can have differences in reactivity like we just talked about. And then you can have carbon bonded to a more electronegative atom. This increases the polarity. Which of course changes the properties. So each time we'll go through those. And you can even have hydrogen bonding as well. So even within the functional groups, we'll look at the differences. So this, for example, and this, we will not classify the same because this can hydrogen bond and this cannot. There's no hydrogen there. Same thing with this. No hydrogen bonding. So we will look at the differences in those kinds of functional groups. And you'll also see carbon double bonded to an oxygen. The good thing about this is that we won't do any expanded octets or whatever. It's going to follow the rules. So carbon will need to have 4 bonds, oxygen will need to have 2, hydrogen needs 1, nitrogen needs 3, so you can follow those patterns. So there's really 2 kinds of tasks for homework today. So this worksheet is from another textbook. And I those of you in my class before, you'll know I almost never assign read the question or read the textbook and do the homework. So that's how important the ideas behind the intermolecular forces are. And I think this other textbook is better than yours. So the questions go in order. I tried to leave a little bit of space. If you have big handwriting, I'm not sure, but you can be as concise as possible. You can write it on the back if you want. And then the other type of, so this is really general. The other type of question from the textbook is a little bit more specific. So we're going to do a couple of examples that are a little bit more like the textbook, a little bit more specific, okay? So are double and triple bonds between carbon atoms more reactive or less reactive than single bonds? So you can even think of this in terms of like changing a double or triple bond into a single. So it's said in the note that single bonds are not often broken. So that's kind of like the bottom of the barrel, I guess. You can't go any farther than that. But double bonds could be changed into single bonds, and triple bonds are even better. Triple to double, double to single. So you can think of it sort of as a progression, and that is the way that we will deal with it when we do the reaction lesson. The section in the note does say both. If you don't like the wording there, you could even write single bonds are strong, so they're less reactive. That's the same thing. Okay, so if you are a visual kind of person, you could even quickly sketch it. So single, again, is it's like the end, okay? So triple could be broken and made to double, which could be broken to make single. So back in the day when we could have guests and there was no COVID, whatever, I had a pharmaceutical chemist who was making medication. He worked at Apotex, which is actually, to be honest, I don't know if it's still there, but it used to be kind of like, when you go to West Brant and then there's that baseball diamond and it's like a weird hill. It's in the bottom down there. And he said that he would often start reactions and 14 hours later would come and check out the product. So single bonds are essentially virtually unbreakable, okay? Except for combustion. That's under the right conditions is readily done. Okay. So then, again, when you do these kinds of questions, there is kind of a variety of questions you could be asked. So this one says, if something is more polar, is it going to have a higher or lower boiling point? So it doesn't say here that, is a polar molecule, does it have stronger intermolecular forces? But that's the reason behind your choice here. Now, this is sort of ruthless. It says less polar. I would probably not make it so ambiguous, I would be asking you to compare polar and non-polar, okay? So that's a little bit more straightforward, hopefully. So when you do your explanation, you have options. So maybe you like to think about, or maybe you spent a lot of time in the first unit really thinking about the strength of forces. So polar molecules have stronger intermolecular forces. So this question doesn't give us a lot of what's going on here. So there's two possibilities, but both of them are stronger than London or nonpolar. So neither of that matters. Yes, right. So in this case, it doesn't really say, like once it's polar, then you have to decide, is it dipolar hydrogen? But we can't really do that. We don't know if it has H, N, or F. We just know it's polar. So polar, whether it's this or this, will be stronger than nonpolar. So you would have to be given more information to say to distinguish between these two. Okay, so polar molecules have stronger intermolecular forces. That means more energy is required to break the forces. So nonpolar molecules will have a lower melting and boiling point. You could have gone the other way, and you could have said nonpolar has weak intermolecular forces. That would be the same support. Okay. So when we go through the families, we're going to look at is it polar or nonpolar? And then we'll look at hydrogen bond. So the next question is more specific. It tells us oxygen and nitrogen and hydrogen, so you know then, oh, okay, yes, that one can hydrogen bond, okay? And what you're also going to see is some of the categories or the families will be the same. So without giving you a lot of data, I can't make you compare them. So for example, we're going to do OH and NH. You don't have to worry about which one of those would be stronger because they can both hydrogen bond, so we kind of clump them together. If something is only polar but can't hydrogen bond, like a single bonded O or double bond O, no H, then again, we would clump those together. I'm not going to make you compare within that, okay? So we'll basically have three categories: nonpolar, dipole only, or hydrogen bonding. So this question here now is telling us, if it has OH or NH, how is that going to affect melting and boiling points. So again, you're looking and checking always, does it have hydrogen bonding? And yes, that is the strongest force. Okay, so if it can hydrogen bond, it's going to make, so in this case, it doesn't talk about um, strength of the forces. Again, it's asking you about melting and boiling points. So the higher the melting and boiling point, the more energy which you would need to break the strongest force. Okay, so this question says the solubility of molecules in polar solvents. I would even usually not make you remember that water's polar. So usually my question would be about water. So you do kind of have to remember a little bit of grade 11, that like dissolves like. Okay, so if something is polar, it dissolves in water or polar. And while you can still go back and do that change in electronegativity if you want, but you're going to see by the end of it, you'll be like, oh, it's basically the same thing every time. It's always carbon and oxygen or carbon and nitrogen that increases polarity. So you'll sort of get used to it. But again, if you want to do the subtracting and you'll get polar covalent, you can totally do that. So polar molecule dissolves in a polar solvent. So OH and NH are polar. So they will dissolve. So basically, we are looking at, um, we're going to look at these properties and these properties in particular because it really impacts humans. Yes. Yes. So if you want, you can do this every time. But really, it's just going to be these ones. Like, you'll be like, oh, it's the same thing. But yeah, go ahead. So, for example, styrofoam. So we're going to talk about the structure of styrofoam. It is a huge organic molecule, very nonpolar, does not dissolve in water. And why does that matter to us? Then we call it non-biodegradable, right? So stuff like that. Things like pesticides and herbicides that are not soluble in water will then dissolve in fat. Animals like us, we are full of fat, full of nonpolar molecules, so they dissolve in us and stay in our systems. So in grade 9, you would have taught, or yeah, grade 9 ecology, you talk about bioaccumulation. You don't talk about necessarily like dissolves like, but it all kind of goes together. Okay, so organic chemistry is essentially the chemistry of life, which is why it's so important. Okay, so you can work on that worksheet. You can do the textbook questions. If you did not get a chance to print off the notes, print them off or decide, it's sort of, yes, there is a little bit of theory, but there's also lots of space for examples. So you could write it out if you want to. You kind of decide what you want to do.